So I'm sending some AC voltage to this diode. My aim is to rectify. Rectify means I want only those signals in the forward direction that can pass through this diode. So the positive side signal will get passed through. And what about this negative signal? When it is in the reverse bias, the diode is not going to conduct. When the diode doesn't conduct, you don't get output. Here you don't get any voltage. So your Vout will be 0. And again, once it reaches the other part, positive signal, a diode will again start conducting. Then you will get another waveform. So it will repeat after every interval of time. So this is what is missing. Here it is missing. So this is up to here, it is 0 to 2 pi phase. You can talk about it in terms of time period also. Up to here you have capital T. Here you have T by 2 time period, half of the time period. Signal waveforms. Okay. Now just let us see which of the following in this diodes are forward or reverse bias. Just our idea is to make it clear. So forward, positive and negative. This diode is and positive being connected to positive. This is positive. This is negative terminal. So positive being connected to positive and negative connected. So this diode is conducting. While the other diode, here you have negative terminal which is connected to the positive terminal of the external battery. It is not connected. Now you have an AC source. At the positive half cycle, this will be conducting. Positive half cycle means if it is plus 2 volt, you write it as 2 volt. 2 volt, and this is negative 2 volt, so it will be conducting. And in the negative half cycle, it becomes minus 2, and here positive. This reverse bias, it won't be conducting. So 0 to T by 2, it will be conducting. T by 2 to T, it won't be. And here in the positive cycle, this parallel combination is used for both way rectification done on both sides, but you will have to use one junction in between to make it in the forward direction, in the same direction, rectification. Now positive cycle, here you have positive here, negative here. This diode will conduct, but this diode will not conduct in the positive half cycle. What about the negative half cycle? Negative half cycle, here you have negative, but this won't be conducting in the negative half cycle. You can write here for positive half cycle, who will conduct? This D1. In the negative half cycle, who will conduct? D2. That means you have an output given for both half cycles. In the earlier cases, what we have seen is, in that cycle, we are not getting output for a certain period. But here, for both half cycle, if you have connected it to a resistance box, you will get output both in the positive half cycle. Okay. Now here, if it is positive, let me write positive and negative, it will not conduct. But what about this one? This is also in the series connection, so this also will not connect. Both will not conduct in the positive half cycle, but for the negative half cycle, both will be conducting. Now you may have one doubt, that is part of the uh, voltage that is being developed across this. For example, I assume this is plus 10 volt, minus 10 volt given to the minus 10 volt given. Okay. Now part of the voltage is being used up by this resistance because current will flow through that resistance. Part of this is being used up. Then when you reach here also, diode will be having some voltage. This diode also will be having some voltage. Let us assume this is 0.7 voltage, 0.7 voltage. Now, so current is moving from this direction. Now, once the potential is developed across this will conduct. Now, there is a drop in the potential here. Okay, if this drop is very large, that means you are getting a lesser voltage here, less than 0.7, for example 0.6 or 0.5. Is it possible? Is it such a case possible? In that case, it will not be conducting. I am asking you whether that case is possible or not in a series connection. It is not possible. Even in any circuit, it is not possible. Why? Because the current it is flowing through this circuit is proportional to the resistance that you are adding. Let us just check for instance. I am giving a 2 volt here. Okay, 2 volt. You have a diode kept like this, and a resistance here, and again a diode. I am applying that Kirchhoff voltage rule. 2 volt is equal to passing through this diode, which is 0.7. I am assuming that it is only having that potential 0.7 volt, plus let this resistance be 2k, 2 kilo. Okay, into I don't know what is that I, plus again 0.7 volt. So the total voltage around this loop is 0. This is a loop. And now what is the current? I is equal to 2 minus 1.4, that is 0.7 plus 0.7 divided by 2k. So 0.6 divided by 2 milliampere, right? Now just see what is the potential drop. Here you have 0.7 volt. I current passing. What happened? Yes. Now to have an equivalent circuit, when we have a diode, how to draw that equivalent circuit? As we have already said, in this diode there is a potential developed, as well as there is a small resistance offered by this diode, the material property of this material. Okay, now the approximate equivalent circuit means we will consider both this V naught as well as RF. RF means if we are using forward bias, RF in our circuit, you write small letter R just to indicate that is a internal resistance of the diode. Okay, now that means when you have a circuit with the diode, just change this diode with V naught. If it is a silicon, use 0.7. If it is germanium, use 0. RF value will be given. Usually this RF value ranges in the ohm, that means 1 to 20 ohms or less. That in that range, it won't be very high. That is an approximate equivalent circuit. All right. Now, uh, once again, what happens is how to identify, or when a circuit is given, which circuit to be used or which equivalent circuit to be used. We will discuss one more, two more. Now another is simplified equivalent circuit. In simplified equivalent circuit, your value of V0 is as usual V0 or VB, but your reverse bias RF is 0. We are neglecting this RF. There is no forward uh, resistance. We are neglecting it for a simplified model. And for an ideal model, both V0 as well as RF is equal to 0. Now here there is a different models for a diode. There is an approximate model, simplified model, and ideal model. On approximate model, the diode is converted into its barrier voltage V0, the forward resistance RF. So this is an ideal diode. So in approximate model, you take the if I can call it as real diode. The real diode is nothing but a combination of ideal diode, RF, that is the forward resistance, and V0, the barrier voltage. So how you get the characteristic curve? It is similar to this. So for up to V0 there is no current, and after V0 the current increases. So this is an approximate model. That means this is how your all diodes in electronic circuit will behave. Now you can consider it as another is simplified model. Simplified model means there is no forward resistance. RF is missing. No forward resistance. No RF. Only there is V0, that is the barrier voltage, and an ideal diode. So how it will behave? There is no current up to V0, and after V0 it shoots up directly, independent of R. Now why it is independent of why when we use the simplified model is, suppose in your circuit other resistance are of high value. Now this RF value, this forward resistance will be 1 to 10 ohms. Okay, and this diode is being used in a circuit where there are 1k, 2k ohm, 2k ohm. These resistance are there in the circuit. Then comparable to this 1k and 2k, this 10 ohm is a very negligible resistance. So we will remove this resistance so that you get a simplified model. And what about ideal model? Ideal model is there is no V0, which means V0 is negligible. This is what you can say, negligible compared to other voltages. V0 value for germanium, you know, this is 0.3. For silicon, you know, it is 0.7. If your circuit is dealing with 20 volt, 30 volt, a higher magnitude voltage sources, then this voltage V0 can be neglected. Similarly, in your circuit, if RF is also negligible, then you get starting from 0, you get a straight line. This is the curve for ideal diode, characteristic curve for ideal diode. An AC voltage has a peak value of 20 volt. Means 20 volt is being fed to the circuit in series with a silicon diode and load resistance of 500 ohm. If the forward resistance of the diode is 10 ohm, find peak current through the diode. Now why it is talking about peak current? Because the maximum current, the maximum voltage is this much. Beyond that you won't get. Peak current means you have to supply peak voltage. So once you supply peak voltage, whatever current you are getting is nothing but peak current. Okay. Now peak output voltage also. Output voltage is means voltage across this resistance. This, yeah. Now how to do this problem? 20 volt will be there. Since it will be having only one diode, you need to consider only forward bias of this. So 20 volt being fed. Okay. Now first of all, what you have to do, convert this into an equivalent circuit. So use silicon diode. So internal resistance is also given. So internal resistance, and as well as since it is given silicon diode, you can use 0.7 volt as the voltage, barrier voltage. Okay, so barrier voltage is also there. Barrier voltage given 10 ohm, that is internal resistance, the forward resistance of the diode in the forward bias 10 ohm. So 20 given. So just applying the Kirchhoff law, 20 volt equal to 0.7 volt plus 10 plus 500 into I. No any other voltage drop. So take this voltage to the other side, 19.3 volt equal to 510 I. So I is equal to 19.3 by 510. Can you give me an approximate answer? Leave it. This is, let it be this much ampere. Now this is for approximate value because we have considered both 500 ohm as well as the 10 ohm resistance. That is, sorry, the 10 ohm resistance as well as the reverse, breakdown voltage. Sorry, which is the break? No, not the breakdown voltage. This is barrier potential. Don't know why I forget barrier potential. We have used both barrier potential as well as 10 ohm Indian resistance. Now they are asking the peak output voltage. So what you have to do? This current will be passing through this 500 ohm. Just multiply by 500. Whatever you are getting is V out. Okay, leave it. So 19.3 divided by 510 into 500. Now suppose if it is ideal, that is the question. If it is ideal, what will be your answer? Before that, let us do what if it is simplified model. Simplified model means this 10 ohm resistance won't be there. So the current after applying voltage, Kirchhoff voltage law, we have 0.7 plus 500 I. So 19.3 divided by 500 will be the current passing. So the voltage V out will be equal to 19.3 by 500 into 500, which is equal to 19.3. Okay, which is greater than this value. Okay, again, what if it is an ideal model? Ideal model means there is no voltage drop across the diode as well as there is no resistance. So 20 volt fed across this output resistance. So 20 volt. Now you can see the difference. Now how to identify which one to use? In the question or question paper, it won't be given whether to use approximate model. If your internal resistance here RF is very much greater very much greater than the resistance used, R. This is R. Sorry, it's not very much less than R. Then you can neglect RF. Okay. If it is of this order, 510, like this, then you can use both. So then you can use approximate model. If it is very much less, you can neglect RF. And what about this voltage? If this voltage is very much greater than V naught, that is barrier voltage, then also you can neglect. Then you can use simplified model. If both this condition is accepted, you can use simplified model. Yeah. So our question is here to find out the current through this diode. Okay, to apply that, it's a problem here. You have to first find out the effective resistance as well as effective voltage when using the current, because current is being divided in this. Now let us first find out what is how to simplify this circuit using Thevenin's theorem. So for Thevenin's theorem we have RT, that is Thevenin's equivalent resistance, as well as VT. Okay, please listen carefully. I am not giving any talk or classes on Thevenin's and Norton's theorem. When we are doing this kind of problems, we will just do one problem and then understand what is happening. Now, to find out VT, Thevenin's equivalent voltage, please listen carefully. Please listen carefully. Imagine this diode is removed. Remove the diode first. Okay. Then once the diode is removed, make it wait 1 minute. Hello. Oh, okay. Hello, can you hear? Some phone call came. I just wanted to make sure this connectivity is okay. Can you hear me? Okay. So here you just have to leave it open. Just keep this open. Just remove this diode and keep it open, and find out the voltage across this A and B. Remove the diode, whatever. If it is a resistance, remove that resistance. If it is a transistor, remove that transistor. If it is a capacitor, remove that capacitor. Keep it open, and across that two terminal, find out the voltage. Find voltage between A and B. This A and B. That will be our Thevenin's equivalent voltage. Okay, let us find out what is that. Now, the voltage across AB is nothing but voltage across this R2, which is 5 ohm. Okay, to find out this voltage across R2, we want current across this terminal, or I mean this resistance. Now, once we want current, we have to do what? Find the net current flowing. Whatever current flowing through this will flow through this, because this is open. There is no current flowing through this diode. I mean, in this way there is no current. All the current will have to move through this. So VT is equal to, first I am finding the current. I is equal to 10 volt divided by 55. That is the current, ampere. Leave it like that. No need to find out in. Now, this much amount of current passing through this 5 ohm. So what is Vt? I into R2. What is that? I is 10 by 55 into 5, which is nothing but 50 by 55. So we got Vt. Don't simplify, leave it as 50 by 55. Now our next question is, find out the effective resistance or Thevenin's equivalent resistance RT. For finding out RT also, first thing you have to do is short the terminal AB. Please listen carefully. Short the AB as well as the circuit, this particular one. Remove voltage source. All voltage sources. Whatever voltage sources you have, remove all the voltage source and short it. Now what is RT then? What is this? Both are in parallel connection. If you want the junction, this is the junction. So R1 R2 divided by R1 plus R2, which is nothing but 50 into 5 divided by 50 plus 5, that is 55. So 50 by 55 into 5. Okay, leave it like this. Now how is our equivalent circuit will be? You have a voltage source of Vt, then you have a resistance RT, and you have a diode. If it is diode. If it is an output voltage, output this load resistance. Here it is diode. Now Vt by RT will give you the current. If you want, you can write I dash. What is I dash? Vt. What is Vt? 50 divided by 55 divided by RT. What is RT? 50 into 5 divided by 55. 55 gone for party, and this 50 1 by 5, that is equal to 0.2 ampere. This is the current through the diode. See, yesterday we discussed about approximate model. This approximate model is also called piecewise linear model. Piecewise linear model. Okay. Now, here this voltage, whatever developed across this, we in the graph, we can draw the slope. Find the slope of this curve. What is that slope of the curve will be? If this is V0 and up to here we have increased the forward voltage Vd, that is the voltage applied across the diode. Okay, voltage applied across the diode, and in that process we have this much amount of current developed across through the circuit or through the diode, that we can write it as Id. Okay, now slope means Id by or delta Id by delta Vf. Now what is delta Id? That delta Id is nothing but the diode current, and delta Vf is nothing but Vd minus V0, where V0 is the barrier potential and Vd is the voltage applied across the diode at particular point. Okay. Now, what is 1 by slope? 1 by slope is, or inverse of the slope is nothing but Vd minus V0 divided by Id. That is nothing but our RF, that is forward resistance, or sometimes it is referred to as RD, diode resistance. So from the graph we can find out RD, that is the peculiarity of this approximate model. In other two models, simplified model as well as in the uh, the last one, what was it? Ideal model, yeah, ideal model, we do not have a RD, there is no forward resistance. So this is applied only in approximate model or piecewise linear model. Okay. Now you can also write dou ID divided by dou VF. This also you can write it as RD. Sometimes in the question you can get ID as a function of V, function of VF. So what you have to do, you just have to differentiate with respect to VF. Okay, this is 1 by ID, not ID. This is 1 by RD. Okay, and voltage between 2 points. Now how to do this problem? Voltage at a point. Let us have a problem here. You have starting with 20 volt and you have a series of voltage sources kept. Okay, and you have VB here or point B. Your aim is to find, or you can write A. You have a point A and you want to find out the voltage at that particular point. Okay, so how will you start doing? Voltage at point A. So mark that point. From that point, go to the other end. Mark that point and go to the other end. I will give you the voltages, or this is 5 volt, 10 volt, 12 volt, and again 5 volt. Now when you go from A to the other end, this is 20 volt which is positive. Okay, and the other end of the 20 volt will be grounded. Now when you go from A to this other end, whatever you are crossing the positive terminal, put plus. If you are going to the negative terminal, put minus. Here again you are crossing the negative terminal, minus. Again you are crossing the positive terminal, put plus. And here 20, plus 20. Okay. Now then VA is equal to 5 minus 12 minus 10 plus 5 plus 20. 5 plus 5 minus 10. So that is gone. Minus 12 plus 20. That is 8. So VA equal to 8 volt. This point, what is the potential means? 8 volt. Voltage between 2 points A and B. Now I have 2 points A and B. Between that I have series of voltages. See, these voltage sources need not be always voltage source or producing voltage sources. It can be a resistance that having a passing a current I, which means R into I is your voltage. Then it can be your diode with barrier voltage V naught, or it can be capacitance. Okay, it can be anything. But in that case, we should see the direction of the current also. We will discuss that also. Now, A voltage source, 5 volt, 10 volt, 6 volt, 5 volt. Now, voltage difference between 2 points A and B means VA minus VB. I am assuming that VA is at higher potential than VB. But let us see, is that true or not? That is nothing but VAB. VA minus VB is nothing but VAB. That is what we have to find. If we are finding from A to B, write down all the voltages with their corresponding terminals in order: minus, plus, minus, minus. Minus 5, minus 5, plus 10, minus 6. So I am writing minus 5, plus 10, minus 6, plus 5. This much volt. Sorry, minus 5. Which is equal to minus 6 volt. So VA minus VB equal to minus 6 volt. That means whatever I have assumed, that is VA at higher potential, is wrong. VB is at higher potential. Okay, so no need, you just have to understand what is VAB, that is equal to minus 6 volt. So what will be VBA? VBA will be equal to 6 volt. If you want, you try from the other end. VBA, in that case you have to start from B and end at A with adding all the voltages with along with the terminals, positive or negative. You will start from B. In that case, this will become positive. This will become positive. This again positive. This minus. This again positive. So, what is the question? Calculate the current through 48 ohm resistance. This is the 48 ohm resistance that we have. Now, first of all, what we have to check? We have to check which all diodes are conducting. Okay, so it is connected to positive, this is negative. So positive being connected to positive, this is diode D1 is forward bias, that means it is conducting. Positive being connected to negative, so D2 is non-conducting, while D4 negative being connected to the positive terminal, D4 is also not conducting, while D3 you have negative connected here, so this is also conducting. So you have D1 and D3 conducting diodes. So we can write an equivalent circuit, can convert this given circuit in an equivalent circuit by changing the silicon diode as it is an approximate model, because your resistance is given as well as voltage. Voltage is 0.7 volt along with a resistance of 1 ohm. So each diode we have replaced it with an equivalent resistance and a voltage source. Here also resistance and voltage source. Now what we have to do is apply our Kirchhoff voltage law along this loop. That what loop we have? See, D2 and D4 are off. So this is the current direction. This is the loop that we have. So 10 volt is equal to, by applying, we have 1 ohm. So I am considering I as the current passing through this circuit, I into 1 ohm plus 0.7, which is the diode voltage, plus 48 ohm into I plus 1 ohm into I plus 0.7. Alright, now 0.7 volt, 0.7 volt, add and bring it to the left side. So 10 minus 1.4 volt equal to 148 and again 1. So 50 ohm into I. So what is I is equal to, current I is equal to, this is 8.6 volt divided by 50. Now dividing by 50, don't do all those calculations and use your calculator. Just multiply by 2 and divide by 2. You will get 17.2 divided by 100, which is equal to 0.172 ampere. This is 0.712 ampere is the current passing through 48 ohm resistance. See, our aim is to find, see, this equivalent circuit, uh, only one diode D1 will be conducting because D1 is forward biased and D2 is reverse biased. And we have an equivalent circuit here with this D2 removed. And what is the Kirchhoff loop? This is the loop. Across this loop, the total voltage should be 0. Okay, just immediately applying that 24 volt is equal to I current, let me write capital I as given there, into 2k ohm plus 0.7 volt, which is the diode voltage, plus I am going through a plus voltage, so first terminal is positive, so plus 4 volt, nothing else in between both of this. So 24 minus 4 minus 0.7, so 19.3 is equal to 2 ki, 2 kilo ohm into I. Now what is I is equal to 19.3 by 2k ohm. Don't write 10 to the power minus 3, something like that, leave it. 19.3 divided by 2 is nothing but 9.65. This going to the upper side, it becomes milli and ampere. The current through the diode is 9.65 milli. So 20 volt. Now our aim is to find which one is conducting. See, silicon diodes needs 0.7 voltage to make it conducting, and this germanium needs only 0.3. Now once you start applying the voltage, this germanium diode will start conducting immediately, because within the voltage, that is 0.7 and 0.3, the resistance of 0.3 is very less. That means all the current will be flowing through 0.3 germanium diode than silicon. So we have a equivalent circuit. So 20 volt with a diode, germanium diode, and you have a resistance of 3 ohm, sorry, 3 kilo ohm, and this is where you have to find out the voltage, that is VA. Now we can apply easily our Kirchhoff law. There actually here you need not even find out the voltage, sorry, current, because germanium diode is having 0.3 volt. Now what is this VA? The entire voltage V minus whatever voltage here we have V dash. If this is VA, that means VA is with respect to the ground. the entire voltage VA is nothing but that total voltage V minus V dash, right? What is V? V is 20 volt minus what is V dash? From here to here there is a drop of only 0.3 volt, so 0.3 volt, which is nothing but 19.7. Now if you want to find out through our usual method, finding I, 20 volt is equal to 0.3 volt plus I into 3 kilo ohm. Alright, I into 3 kilo. Now what is I? That is equal to 19.7 divided by 3 ko, or that is nothing but 19.7 divided by 3 milliampere. Now through which I want the voltage? I want the voltage across this resistance. I into R will give you voltage V. So V is equal to, what is I? 19.7 by 3 milliampere into 3K ohm. Milliampere and K goes for party, 3 and 3 gone, V is equal to 19.7 volt. So here is what we have. 10 volt battery supply. We have a bridge like circuit with both the silicon diodes and connected in series with a 2K ohm resistance, and again 2K ohm resistance at the end. Now what is the question is, you have to find VQ. VQ is with respect to ground, this voltage, that is nothing but the current into the resistance 2K, current passing through the 2K resistance, the product of that will give you VQ. And before that we have to find out ID, the current through the resistance diode. Now in the beginning we have to consider an equivalent circuit for this with a loop. The plus voltage is here, the other end of the negative terminal is connected to the ground. Now you have an equivalent circuit here. Now 2 times ID current is passing, 2 ID current is passing. It's just an notation to understand that each branch is taking away ID current, ID in both the branches, such that it is divided among both the branches equally, because you have equal volt diode and an equal resistance in both the cases. Okay, now what we have is it is flowing through the circuit making a complete loop. So let us take any one of the branch and find out this voltage, or let us find out first ID. All right, and we have to use simplified model. Simplified model means only no resistance, only the diode voltage V0, that is the barrier voltage V0 we have. So let us apply. So 10 volt is equal to, I am using the first loop, 10 volt is equal to ID moving, so 0.7 volt plus 2K into ID, 2K into ID plus, now once it reaches here it is no more ID, it becomes 2ID because the current through this also passes through the same. So plus 2ID into 2K ohm resistance, nothing else across this. Alright, now 9.3 volt is equal to 2k ID plus 2k into ID. Sorry, 2k into 2 ID. So 4k ID. So which means 6k ohm into ID, which means ID is equal to 9.3 divided by 6. Leave it like this, 6k ampere. All right, this much ampere. Now what is the question? If you want, you can simplify this and write milliampere. So what you are getting is 3.2, what is that, 3.1 divided by 2k, which is nothing but 1.55. K goes to the numerator, becomes milliampere. Fine. So that is okay. Now I want the voltage across this resistance 2k. Nothing, just multiply by the current that I have. What is the current I have? 9.3 by 6 k ampere into 2k ohm. 2k ohm. K gets cancelled. Here becomes 3, 1, 9.3 divided by 3, that is equal to 3.1 ohm, and ampere, that is volt. 3.1 somewhere missing, 2k ohm. Wait. Now this is not actually, what is the current passing through 2k ohm? This is 2 id. 2 times id is the current passing through this one. So it has to be 2 times id. So multiply by 2, you get 6.2 volt. Sorry for that mistake. I hope you understood. id is the current passing through these phases, these places. Across this 2k ohm, it is 2 times id. I hope that point is clear.